All right, today we'll be spending our time talking about well hydraulics. We have talked about governing flow equations in Cartesian coordinates, XY coordinates. We will essentially now look at well hydraulics, where we will primarily be using radial symmetry to simplify the problem. And you have the handouts. I do want to say that the handouts were prepared earlier, and the presentation has undergone some correction and changes. So please be aware of them. So you'll see some of the things are different in the presentation than they are in the handouts. Okay. So let's get started by looking at the general equation first for, movement towards a well, in the subsurface medium. And we have the typical the typical terms, just that we are exploiting the fact that the variation is only in the R direction, which is going to be, R is a distance which is measured radially from the center of the well to some point. And for radial symmetry, angle theta does not matter. So in other words, there's no changing that's occurring in theta. There might be variation in Z, the vertical direction, but for most of the topics that we are looking at, we will assume essentially horizontal flow. Okay. So this is going to be our typical equation. H is the piezometric head that we have talked about before. The conductivities, and R and Z are the directions that we are looking at, as the spatial directions. You will notice that because of this is the flow coming, let's say, towards the well. And if you think of because of radial symmetry, if I draw a cylinder around the well of a certain radius, as this radius becomes smaller and smaller, the area through which the flow is coming towards the well is becoming smaller and smaller. So the fluxes, mic is on, but it's not. The battery is weak. So you can imagine that as you come closer and closer to the well, the amount of water that is having to cross this area, the area becomes smaller and smaller, even if the amount of water will be changing. And therefore the fluxes increase. So there is a lot of concentration of flow, which some people term as radiality of flow. And of course, as you go further and further and further away from the well, the flow tends to be less focused in some sense. Okay. I also want to know that when you write equations of this nature in radial coordinates, R will appear in the denominator in some of the terms. And what also means is that R cannot theoretically or physically go to zero. Because at that point, we would say we have a singularity. But this equation, therefore, is actually applied in principle from the radius of the well outwards. Even though sometimes we look at limiting behaviors when we say, well, what if the radius of the well is very, very small, R is tending to zero. So we will keep those things in mind. We'll start by talking about axisymmetric flow in a confined aquifer. So confined aquifer, we are looking at essentially horizontal flow. Okay. And in this figure, this over here, what you see in the bottom is a confined aquifer, has a thickness B. A constant transmissivity is one of the assumptions that we will make as we go along. So if this is the main aquifer with thickness B, notice that from the well, we are pumping some water Q. Okay. Let's say before pumping started, the original piezometric surface was given by this dashed line. And as pumping goes on, there we create a cone of depression. So the piezometric surface is going to have a depression, and water is therefore coming into the well in response to this gradient. So that if we were to essentially have, let's say, observation wells, which are tapping into the main aquifer, the heights to which water is going to be rising in the observation wells gives you a sense of where the piezometric surface is. And so R is the distance then measured from the center of the well to some location. And at that location, depending on where we choose the reference, small h is essentially the piezometric height. So if we have R1 and R2, these are different differences then, or different locations. Basically the difference from the original piezometric surface to where the drawdown has occurred and the new piezometric surface, the fall in the piezometric surface is what we call as drawdown small s. So obviously small s is also going to be changing with the distance from the well. It's going to be highest right at the well, where if we were to drill a well and have and find the height of water, let's say that height is h sub w, okay? And therefore the drawdown at the well would be the value of s at r equals r sub w. Okay? And in this instance, as you see h sub 0, if that is the initial piezometric surface height, and let's say that is horizontal, then of course s at any location and perhaps any time also is going to be h sub 0 minus the current value of h. So our usual definitions, T is going to be transmissivity and H is the piezometric head. S now is the aquifer storativity because we are talking about essentially horizontal flows. So this basically sets up the notation for us. We can do the same thing for an unconfined aquifer. We would have a similar equation. Notice that the variation in Z is gone. We are talking about flow throughout the thickness of the aquifer. Somewhat similar terminology. The height of water in the well is, let's say, h sub w. And let's assume that h sub 0 was the initial height of the water table or the piezometric surface. After pumping starts, perhaps at some other time, the shape of the piezometric surfaces or the water table is given as such. So again, we have created a cone of depression because of the water table. And then the slope of the water table or the piezometric surface is moving water towards the well. And then we have similar definitions for H and the drawdown that we have for the unconfined aquifer. We are also going to be making some assumptions which will not repeat all through. One of them is, if we have an unconfined aquifer, as the water comes close to the well, H sub W is the height of the well, there will be a seepage phase formed, and therefore the water table actually intersects the well at a certain height above the height of water in the well. We will neglect that seepage phase. For confined or unconfined aquifers, there is also a matter of at the well, there are going to be some other well losses based on the well casing and the packing and so on that has gone. So we are not going to explicitly account for those, even though one can do that should they so choose. So the expressions or solutions that we get when we impose boundary conditions at the well and say, well, at r equals r sub w, if I think the piezometric head is going to be h sub w, then of course our solution will come and join at that height. But as I said, there will be some small errors that we'll make. Okay. So this helps us establish the notation, and you will notice that the storativity term has both compressibility effects, S, and specific yield effects, S sub Y, for unconfined aquifers. Okay. We can also look at what happens when you have a leaky confined aquifer, just to see how the equations are going to develop. So in this case, this is the main aquifer. It is confined, it has leakage. On top of it is an aquitard, so semi-confining layer, okay, through which leakage can occur. And this is the height of the water table initially, okay. And the piezometric surface within the main aquifer is given by this dashed line after some time of pumping. So at a distance small r, the drawdown that we are experiencing is S. So from the initial piezometric surface, how high, the piezometric surface has fallen. Okay. And of course, depending on the nature of the aquitard, we are going to have leakage either into or out. Depends on whether the piezometric surface within the confined aquifer, whether it's higher or lower than what it is for the unconfined aquifer. The way it's shown right now, leakage is occurring from the unconfined aquifer with a water table on top into the main aquifer. So for the main aquifer then, if I were to try and write the governing differential equation in terms of transmissivity, H is the total piezometric head, W of L is the amount of water that I'm withdrawing per unit area per unit time from the main aquifer, and this term accounts for the leakage. So this is proportional to the difference in heads. H is the head, for the unconfined aquifer just on the other side of the aquitard, and of course small h is the piezometric head within the main aquifer. So that difference divided by C, and we will notice that C is given as B prime over K prime. B prime is the thickness of the aquitard, K prime is the vertical conductivity of the aquitard, okay, called as hydraulic resistance. Of course, if that resistance is infinite, either because the conductivity of the aquitard is 0 or because the thickness is very, very large, then of course there is no leakage. The water table on top, the unconfined aquifer, in principle, you could have another equation for water movement in the unconfined aquifer. Okay. Here again, K's would be the conductivities. Notice that for this particular aquifer, if G is the distance from the reference to essentially the bottom of the unconfined aquifer, the flow thickness then is going to be capital H minus G. And therefore, you make that correction. And then in this case, the leakage is going to be leaking the unconfined aquifer into the main aquifer. So you have a negative term multiplying the leakage term. So those will be the governing equations. If we assume that while leakage is occurring, that the unconfined aquifer or the aquifer on the other side of the aquitard is not being affected, the water table height is not substantially changing in this case. Okay, and we assume, let's say that therefore there is no appreciable movement of water in the unconfined aquifer, then we don't actually need this entire equation. We are basically saying capital H remains a constant, and that simply governs leakage into the main aquifer. We don't need a separate equation to describe what's happening, on the other side of the aquitard. So we make that simplification sometimes too. So these basically are the kinds of governing equations that we have for well hydraulics, and solving them, for all complex problems typically will require some numerical methods. However, there are many instances where we are able to use simple analytical solutions. Either we are able to approximate the solution to approximate the physical situation to get an analytical solution, or we are able to make some assumptions. And in fact, we'll be focusing most of our talk today on some of these simplifying cases for which, let's say, some sort of analytical solutions or simple solutions are available. So we'll start with steady radial flow in a confined aquifer. So again, the confined aquifer is below over here, as you can see. And then this is the well which is pulling water out. There's a ground surface. Let's say this was the original piezometric surface, which is shown as a dashed line. And then after pumping starts, okay, this basically shows the piezometric surface or the drawdown curve. And since if we assume steady state, then the time dependent terms are gone, okay, and we would have this equation. Further, if there is no withdrawal from the main aquifer except from through the well, W would be 0. If capital T, the transmissivity is constant, it's a homogeneous aquifer, then essentially T will cancel out and you will get an equation which looks like this. Okay. Simpler equation, which is, which will admit some solutions. Notice that it's still a solution it's an equation, second order differential equation in H. So it will need two end conditions to be able to specify the solution. And we can choose, or we decide where we want to specify those, those end conditions. We will also note that any distance R, the flow that's coming in towards the well because of radial symmetry, the area through which it is coming is 2 pi R times B. If the conductivity is K, then this is K times the area, this is the gradient, okay? And K times B is transmissivity. And what we are going to do is, typically, if you recall, we have a minus sign here. But we are going to now say that Q is positive if water is coming towards the well. That means Q is positive if it's moving in the negative R direction. So we remove that negative sign and say this is what will define Q as being positive when it's in the decreasing R direction. And then if for steady state, no leakage, nothing happening, then this Q is going to be constant. In other words, at any distance R, whatever cylinder I draw, the water coming in has to be the same. So much so that when R equals R sub W, that should equal to the water that's being pulled out of the well, Q sub W. So basically this becomes typically one of the boundary conditions. The other boundary condition is a little more, you have to put a little more care in it in some sense. What I will say is, let's say we have many observation wells. Let's say we started pumping, and for simplicity, let's say this pumping rate is a constant. This cone of depression will develop, and after a certain time, it achieves a steady state. If we were able to place observation wells continuously at different distances, after a certain distance, we are not going to be able to see any drawdown, no appreciable drawdown. So if we were to monitor continuously with increasing R, as you can see, the drawdown slowly decreases, and eventually comes to a point where you can't observe any drawdown for that withdrawal rate. So for that withdrawal rate, we will call that as capital R, also called as the radius of influence of the well. So we could, for instance, apply another boundary condition and say at small r equal to capital R, the piezometric head is equal to capital H, the original piezometric surface, or that drawdown over there is 0. And then we would basically say that, the drawdown somewhere else is capital H minus the piezometric head at that particular value of R. Okay. But at capital R, the drawdown is 0. So that's what's stated over here. At some distance R, minimum distance R, beyond that R and beyond, there is no drawdown. We call that as the radius of the well. The piezometric head over there is capital H. And then, of course, we can solve this equation. Since we have, R times dH dr, we have a log term in R. The drawdown, by applying that equation between some small r to when small r equals capital R, gives us this equation. If basically I substitute R equals R sub W, then this becomes this particular equation. So at the well, we will have the maximum drawdown, which is, this equation which gives us a drawdown at a particular distance is called the Thiem equation. This is one of the simpler solutions that we have. What happens when we have an unconfined aquifer, steady state again? So for 1D axisymmetric flow to a fully penetrating unconfined aquifer, and again, we have the symbols over here. H sub 0 is the initial water table height. And let's say for now, for steady state, that means the pumping is constant. After pumping started, the drawdown cone has developed, and after a while it's not changing. Then that becomes, our steady state. And then we are able to talk about what the drawdown would be at different distances. So with all these assumptions, and again taking W equals 0, the aquifer is homogeneous, steady state, we'll get an equation like this. Now, this equation, as you will recognize, even though it's nonlinear in H, it is linear in H square. So we can make that transformation, and we'll be solving a fairly simple problem. Okay. We will again set a boundary saying that at some distance away from the well, no appreciable drawdown, no change in the water table. We'll call that as, let's say, the radius of influence of the well. And we can again write an expression for Q at some distance R, at any distance R. This R, of course, has to be within the radius of influence. And we would get this expression. And Q is going to be a constant for steady state. So if I set R equals R sub W, Q would actually be equal to Q sub W. This remains constant. And if we solve that equation, we are essentially going to get this as our solution. You will see we have a H dH, so you'll get an H squared when you integrate. And you have dr over R, which gives you this log term. So that is a simple solution. And the solution now is in terms of capital H square. It's possible to rearrange it a little bit. we notice that we have defined the drawdown as capital H minus small h, so that if I expand this term over here, I'll have H plus H times H minus H. H minus H is what we call as a drawdown. Small h plus capital H, if the drawdowns are small, okay, that means at almost all locations, small h is very close to what the original piezometric head was. We can sort of approximate small h plus capital H by this quantity 2 times h, and then write k times h as a transmissivity, so that we would get an approximate solution for the drawdown S in this form, which basically resembles Thiem's equation. However, it's fairly easy to use this equation directly and get an expression directly for H, and then subtract this value from the original capital H and you would get the drawdown as well. Any questions? Okay. Well, let's look at a slightly more complicated problem. Still steady state, but now we are looking at a confined aquifer with leakage. So there are some interesting things that we are going to observe. First, the equation. We are not going to spend a whole lot of time talking about the equations. They are all solved in a similar fashion, a little bit of mathematics. You'll have to use boundary conditions and so on. But notice that because we have the leakage term, so we have a source term, because the way we have shown the figure, water is entering the main confined aquifer, and the rate of leakage is proportional to the head difference, H minus H, and divided by C, the leakage factor. And in this case, I'm already assuming that irrespective of this leakage, nothing is changing in this aquifer above. Okay, so the water table is essentially staying over here, and it's not being affected irrespective of the leakage. So there are a couple of things that are of interest, and we will make the simplifications that the aquifer is homogeneous, therefore the transmissivity is constant, capital H is not changing, so we don't have that second equation telling us what is happening in the unconfined aquifer. H is constant. A couple of interesting things, like I said. One is, in the previous examples, when we did not have leakage, the flow that was coming towards the well at any distance r, to that cylinder r, was not changing. But because now we have leakage, that means water is entering the aquifer, in this case vertically, so the amount of flow that's moving towards the well is going to be changing with r now. At some distance r, you have a certain amount of water coming in from that cylindrical surface, but as you come closer, all this leakage water is also being added and being pulled towards the well. So that as I come closer and closer to the well, the amount of flow that's coming into the aquifer towards the well is increasing. And this is, of course, assuming that the leakage is in some sense positive. It's adding water to the well or to the aquifer. If on the other hand, leakage was leaving the aquifer, as it came closer and closer to the well, you would have less water coming in towards the well. Okay. The other phenomena that you see is, assuming that the aquifer is of, let's say, infinite extent, large enough, after we go far enough from the well, if this is the water table, the piezometric surface will go and join this water table. Piezometric surface of the confined aquifer will eventually go and join what the water table height is. Can anybody tell me why? Why should that be the case? Do we all understand that as we change the distance from the center of the well, the total flow coming to the well is changing because of leakage? Is that clear? So why do you think that the piezometric surface should eventually go and join the water table? What would you expect physically to happen? What is the leakage actually doing? So what the leakage is doing is, if the piezometric surface on the other side of the aquifer is higher, it's going to pull water in. Okay? But as we keep going further and further away, notice that the piezometric surface in the main aquifer is rising. And therefore, as I keep going further away, the leakage rate is essentially going to be affected too. If it's going to achieve a steady state and be at equilibrium, this leakage will keep happening until both the piezometric surfaces on both sides are essentially the same, and then it will stop. And you have to go that distance to say, well, that is approximately what we would think of as radius of influence. I'm sorry, my mic is going on and off because the battery is very weak. All right. So again, we'll define our drawdown as this change in the piezometric surface from the original height, which we'll take as the water table, and the piezometric surface after some steady state has been achieved. But this is our governing equation now. Okay. And for the assumptions we have made with constant transmissivity and so on, we'll get an equation like this, where C was the leakage factor. C times T is called as a leakage factor. Sorry, the square root of C times T, L, is called as a leakage factor. So now that's a property of both the aquifer and the aquitard. Okay. So transmissivity, property of the aquifer, C is coming from properties of the aquitard. And we can rearrange this equation to get an equation of this sort, which has somewhat more complicated solutions. So general solutions are in terms of Bessel functions. And we don't have to understand all the properties of the Bessel functions, but just that this is what the solution looks like. Okay. And alpha and beta are going to be two constants then that we would have to satisfy based on two end conditions. I0 and K0 are the Bessel functions. Okay. So the first kind, second kind of zero order. So Bessel functions, if you're familiar with them, that's great. If not, they are they're not quite like sine and cosine functions, but if you recall, sine and cosine functions are sometimes what comes out as general solutions, sometimes exponentials as the general solutions for which we have to find particular solutions based on end conditions. So Bessel functions, but they are also fairly well tabulated, and they have certain properties. The boundary conditions that we would then apply are that when R is tending to 0, if R is tending to 0 in the previous equation, if R is tending to 0, this quantity I sub 0 of 0 is 0. So, so that is, we know that the drawdown is going to be 0, at a certain distance from the well. So as R tends to infinity, some far off distance, there is not going to be any drawdown. Right. There would have been essentially equilibrium between the piezometric surface in the main aquifer and in the unconfined aquifer. So our solution, by applying that condition, simplifying to this, the other condition that we apply is at the well. So at the pumping well, if QW is the pumping rate, then we see what is the flux coming into the well at R equals R sub W and set that equal to Q sub W. And if we do that, we are essentially saying when R equals R sub W, we have this particular expression and for the drawdown, and then we can make those substitutions and therefore calculate beta, and we'll get an expression of this nature. So once beta is known, we can substitute it back and get an expression which tells us what the drawdown is at a distance R, but now it's in form of a modified Bessel function of second kind. We can also look at typical values that we have for the leakage factor, for the radius of the well, and see that RW over L, RW is radius of the well, L is the leakage factor. That tends to be a small quantity, and it so happens that X times K1 of X, K1 is also a Bessel function. Who says? All right. So we make this substitution. Say that typically the radius of the well is much smaller than this capital L. And therefore, we make this particular simplification that when x is small, x times k1 of x is nearly equal to 1. So that in our previous solution, if Rw over L is very small, then Rw over L times K1 of Rw over L, this quantity is nearly equal to 1. And therefore, we end up with a much simpler solution or expression for the drawdown. Further, further if R over L, that means if I'm looking at small distances from the center of the well, if that is also small, then K0 of x can be, if x is small, K0 of x is approximated by this particular expression. And we get a certain amount of error. So for small distances R, we can write the drawdown as this particular expression. Fairly simple expression now. Looks like what we had as an expression for a confined aquifer drawdown in the same equation, if I could replace L times 1.123 as the radius of influence. So L, leakage factor, is an important length scale. But we get an expression for what the drawdown is for a leaky aquifer under these conditions. Unsteady radial flow to a well in a confined aquifer. So we spoke about some steady state solutions, which are fairly simple. For unsteady flows, now we have the time derivative term, and we are talking about a confined aquifer first. So we'll again make some assumptions, assume that, the flow is essentially one-dimensional, transmissivity is a constant, W is 0. We essentially get this particular equation. And so this is a second order equation, but it's a partial differential equation. H is now a function of both R and T. We will assume that the initial pumping surface was, an initial piezometric surface was horizontal. The aquifer is essentially infinite in extent. The radius of the well is small, so that there are no storage effects within the well that we have to worry about. We can define the drawdown then as capital H minus small h. And if we were to make this substitution, our governing equation is now in terms of small s to drawdown, okay? And has the same form as the equation in terms of h as well. Okay. But now this requires two conditions in space, because it's second order in space, and an initial condition in time. But we have already said that initially we will assume that the piezometric surface is horizontal, okay? So that this is essentially our drawdown. So our initial condition is that at time t equals 0, the drawdown is same everywhere. And then with time and with pumping, we are going to see how the drawdown changes at different distances. Okay. The other boundary condition that we apply, one of the boundary conditions that we apply as time keeps changing, is that at R equals infinity, there is no drawdown. That's a simpler condition. And then based on the pumping rate at the well, we will essentially have QW, which is the pumping rate at the well. And so that becomes our other end condition, that at R equals RW, the rate at which I'm pumping QW is given to me. So I'll use that as my condition. So this equation with these conditions is not straightforward to solve, requires a little bit of work. It uses, the method uses something called similarity transformations, which is one of the ways of solving differential equations. Essentially what it means is, it so happens that for this kind of problem, even though R and T are independent variables, so for different R and different T, we should get different drawdowns. The combination R square over T, So even for irrespective of different R and T values, as long as R square over T is the same, they'll all have the same drawdown. So that's called a similarity transformation. So we have small r square over T, and for mathematical convenience, we define this new variable U, which is r square over small t here. I'm multiplying in the numerator by capital S, so storativity, and the denominator by 4 times capital T. So notice that storativity and capital T, and of course 4 were constants. But the important thing is for r square over T, so that becomes a similarity variable. So even though it's a partial differential equation, if you were savvy enough and used the similarity transformation, you would convert it to an ordinary differential equation, which you could then solve fairly easily. But people have done that and have given us this expression. The drawdown as a function of R and T is going to be QW, which is the pumping rate in the well, divided by 4 pi capital T. And then this quantity over here, integral from U to infinity e to the power of minus x over x dx, where U, of course, is what we talked about as a similarity variable. X over here is a dummy variable. That means this part over here is going to depend only on U. Okay. So this function is called the well function. Well functions are, I'm not quite sure if it's available as a built-in function, but tables of well functions are easily available. Okay. So what we have then it means is, given S and T, now we have to also be careful. Capital S is the aquifer storativity. Small s is the drawdown. They're not the same things. So one needs to watch out for the notation. So if we keep using U, then of course U has the storativity and the transmissivity. It has time and it has R. And then the solution depends on different values of U. The well function then has to be given to you. So the well function is also sometimes for this relationship between U and W of U, that has nothing to do, it's a mathematical expression. It has nothing to do with what pumping is happening, what transmissivity, what storativity. It's a fixed mathematical function, sometimes called a type curve. And if I plot W of U versus 1 of U as over 1, W of U as a function of 1 over U, as shown over here, you'll get this fixed relationship. Okay. And so that is a fixed function. It's called type curve. And what it also means is, if I had this curve available for a given R, given T, given storativity, given time, I could find U, I could find 1 of U and 1 over U, and then figure out what W of U is, or look up tables. Well function, of course, we have said it is this particular integral, U to infinity e to the power of minus x over x dx. Okay. As U becomes large, this approaches 0 fairly fast. If I were to do term by term expansion of the exponential function and integrate each of those terms, I would get a long series. And you can see that, you have the first 2 terms, and then you have U squared, U cubed, and so on. If U is small, these terms are going to become small very fast. So that for small U values, we are able to retain, let's say, just the first 2 terms and get an expression of this nature, which tells us what the drawdown is as a function of R and T in terms of the well pumping, the transmissivity, the storativity, and of course R square over T. This approximate solution is called as Cooper-Jacob solution or Cooper-Jacob equation. And we use that quite often. Okay. If we have unsteady flow in a leaky confined aquifer, the aquifer is still unconfined, but now we have added leakage to it. And again, we are assuming that when the leakage happens, the piezometric surface on the other side of the aquifer, the semi-confining layer, is capital H, and that's not being affected by leakage. So we are assuming that to be a constant. You would get this particular equation. You can make the substitution that small s equals capital H minus small h. And in this case, we have realized that the transmissivity is a constant. We will get an equation like this. The initial condition is at time t equals 0, drawdown is 0 everywhere. We apply, the boundary condition that at some distance infinitely away, drawdown is 0. At the well, we have a certain amount of drawdown, or not drawdown. The drawdown is given, and that is going to depend on how much water we are pumping from the well. And for that, again, we would have a solution, but now a similar solution, but now we have essentially two things to worry about. We have this extra R over L factor also, where L was, what we had defined earlier. If L, this quantity, which depends on the aquifer and the aquitard, if that tends to infinity, that means leakage is not playing an important role. And we would simply get back the original well function solution. Okay. Otherwise, you have to basically do a correction to the well function and get this term added in. So similar to what we had a type curve, which was essentially, if there was no leakage, it would be one single curve. Now that we have different values of leakage, we'll have different type curves, as you see over here. And of course, as the, as R over L values become extremely small, you basically, the effect of leakage is going to be diminished. What it also means is, if you want to now solve or look up the drawdown for an R and T, you have to find U. You also have to have R over L. On the R over L curve, figure out what 1 over U is and find what the well function is. So it's a more complicated well function. Okay. But these curves are available. You'll notice that when 1 over U is small, all these curves essentially coincide. That means for 1 over U small, leakage is not going to be an important factor. And if you recall, 1 over U is given by this quantity. So 1 over U, that means at small, small times T, or very large distances R, this is going to be small, and all these curves will essentially be the same. But at later times, we will have the effect of leakage becoming more prominent. Unsteady flow to an unconfined aquifer, this tends to be a little more complex, even to get, let's say, simplified solutions. So the governing differential equation will look like this. Similar terms, we now have two kinds of storativities to contend with. One is the aquifer storativity, one is the specific yield. So this is primarily being caused by the compressibility of the aquifer. S is compressibility of the aquifer, S sub y is specific yield. Okay. And so S and S sub y, let's say we keep them together for now, and we make the usual assumptions. Let's say W is 0, the transmissivity, homogeneous aquifer transmissivity or the conductivity in this case is constant. And we have assumed that the bottom is horizontal. We have chosen that as a datum. So with all those, and if the water table fluctuations are small, so that the KH term can be approximated by K times an average value of H, which then begins to look like a transmissivity, you would get this particular expression, which is actually the same equation for a confined aquifer, where we have replaced S with S sub y. Therefore, we have already assumed in this case that S, the compressibility effects, if they were negligible compared to S sub y, this is the equation you would get. And then, of course, you would simply apply the well function solution and replace S with S sub y for the well function solution. Same mathematically. So if all these assumptions were met, then this solution would be possible. But what actually happens, or what's typically observed in reality is, this is, if only aquifer storativity were involved, S, you would get this as the type curve in the Theis, method. If we were essentially only going to be using S sub y, we would get another kind of a type curve. When we essentially look at what is happening in an unconfined aquifer, the drawdown essentially follows what it is initially for a confined aquifer, kind of an approximation, and then has this delayed yield over here. So things are different, and then it finally, after some time, goes and joins what we expect for an unconfined aquifer. Okay. So basically, the assumptions that we have made are not allowed, are not working, because what is happening in reality is actually fluctuating between these two curves. At small times, it tends to be closer to this curve. That means all the water is being released primarily from compressibility effects. After the specific yield is fully realized, it takes certain time for the water to be extracted from the pores. Then it begins to approach what you would expect from S sub y, an unconfined aquifer. So in between, there is certain time lag between the water table falling and all the pores in that space draining as much water as they are able to achieve the full S sub y value. So the reasons for this discrepancy are that there's a delay in realizing the full specific yield is being neglected, and the fact that because of aquifer compaction, the water that is coming in initially, that is not being taken into account if we just assume S sub y. So this requires further corrections. And so what Bolton's method essentially says is, well, we need to add another term over here to account for this delayed yield from the unconfined aquifer, delayed gravity drainage. So as the water table falls, all the water is not instantly available for us to pump out. Some of it is going to be available or is going to go and actually recharge the aquifer as the water table is falling. Okay. So we have to say something about what y of t is going to be. We'll again substitute for drawdown capital H, small s, which is capital H minus small h. We'll get an equation of this nature. And now we have to say something about how to model this part over here to account for delayed yield. Okay. And one model that is suggested by Bolton is this. So it says y of t is going to look like this, where the rate at which the replenishment is, or the delay is taking place, is governed by this factor 1 over alpha. Alpha then depends on the nature of the porous medium. Okay. So that would have to be supplied to us. And if we think this is what is happening, then of course, as the water table is falling, as the drawdown is occurring, the ultimate recharge is if all the delayed yield was being utilized, then for this kind of a drawdown, we would expect this term, if all the time were allowed, these two to be equal. That's how we want to define y of t. Okay. So decline in water table head, there is an instantaneous yield because of aquifer solutivity, but the delayed yield is because of not being able to achieve specific yield right away. And of course, with that mathematical expression, I won't go into the details, they are shown over here. We are simply integrating it. It's an exponential expression. We can integrate it so that we would get an expression of this nature. And this allows us to correct for this delayed drainage. Again, the mathematics are given over here. You can look it up. And then we can apply our boundary conditions as we have done in the past, that the drawdown at infinite distance is 0, whereas at the well, the rate at which we are drawing water from the well will act as a boundary condition. So now we get an expression of this nature, 4W by 4 pi t, but now you have a lot of parameters that are governing the drawdown because of delayed yield and so on. So UA, which was our original similarity transformation, assuming that the storativity is the aquifer storativity for compressibility effects. U sub y, again this similarity variable, but now S is S sub y, the specific yield. And then we have R over B, as defined over here, and N, which is essentially the total release by instantaneous release from storage. If S sub y, the specific yield, is much, much larger than S, then N tends to be very large, and that effect is maybe neglected. But as the total solution, you would have to then have curves or tables which are prepared for all of these variables. Okay. So given all these parameters, given the pumping rate, a distance, and a time, aquifer parameters, you would basically then have to look up some complex set of tables to get this. Still a problem because now we're talking about all these 4 parameters. Wharton contributes a simplification to this problem. Assumes that S sub y is much, much larger than S, therefore N is not an issue. And essentially he says that at early time, I'm going to define my U, the similarity variable, as AY. U at A at early times is essentially being given by compressibility coming from storativity coming from compressibility effects, but at later times because of specific yield. So same U, but it has different values depending on, whether we are at early times or at later times. And then created a whole set of curves which now span these two extreme curves. The one that is essentially for compressibility effects, one that is essentially for just specific yield effects, and then all these in between for different RB values. Okay? Which basically means that if you are given R and T and properties of the aquifer, you find R and T, you find U sub A or U sub Y, and a given RB, you essentially go to that curve and find the W value. So still using type curves. Okay. All right, let me try and tell you a little bit about the idea of superposition. Okay. So in an aquifer, essentially what we are doing is we are pumping water out. So we are stressing the aquifer, that's our forcing function. What we are observing are the drawdowns, those are the responses. And we know that for different pumpings, therefore we are going to get different kinds of drawdowns. However, we have the advantage that our drawdown, S R of T, is going to be a linear function of Q sub W. Okay? And U is, of course, is a similarity transform variable. So what that means is, because it's linear, we can superimpose. Superimposition basically says that my drawdown, if the pumping rate is doubled, the drawdown is simply going to double. If the pumping rate is half, the drawdown will scale appropriately. It also means the other part of superposition is, if I already had an existing drawdown and I changed the pumping and added higher pumping, then this change, the effect of this change, will start at the time when this change occurred, and then will simply add to the previous one. Okay. So that's what superposition does. And we will see what that means. So let's say we have a constant rate of pumping for Q1, then we stop pumping at time T1, then at certain time later, T2, we again pump, but at a different rate Q2, which we start and then stop this pumping at time T3. Okay, so Q1 and Q2 are not the same, and then we have the starting and pumping times. What we are given is that our drawdown as a function of R and T is given by an expression of this nature. So when we start at early times, based on this Q1 pumping rate, I would have this as my drawdown. What we are able to do, at least conceptually, is this pumping pattern, we are able to sort of simplify it and say, let's say I had pumping Q1 first occurring infinitely in time, and for infinitely long. But at time T1, to basically have the effect that I'm stopping pumping, I basically have a new pumping rate, which I call as minus Q1. Okay. But it starts at time T1. So the combined effect of these two is there is no new pumping occurring or no pumping occurring after time T1. Then at time T2, I have this plus this, but now I add the effect of this change. Okay, so we are starting with this. At time 0, our change was that we added a pumping of Q1. At time T1, the change was minus Q1. At time T2, the change was a plus Q2. At time T3, the change was a minus Q2. So every time we change, we assume that whatever we started previously will keep on, but we simply add that change. So effectively, to find pumping, because of this pumping pattern, I'm going to superimpose or add the effects of the pumping patterns you see in 2, 3, 4, and 5. And that's what superposition does. So at any time, let's say later on over here, sometime T is going to feel the effect of pumping from Q1, from minus Q1, from Q2, and minus Q2. However, if I'm looking at some time over here, let's say the effect of Q1 did not start at time T equals 0. It started at time T1. So the elapsed time, if you will, is T minus T1. So we'll make that adjustment. And if you were to do that, we would essentially have this kind of a pattern telling us what the drawdown is. So up to time T1, essentially this is my pumping rate. Only Q1 was in effect. Between T1 and T2, now you have the effect of Q1 and then minus Q1, but the effect of minus Q1 is felt over a time of T minus T1 only. Between T2 and T3, we have Q1, the effect of minus Q1, we are adding the effect of Q2, but the Q2 effect is felt for a time of T minus T2. And similarly, for some later time, between 3T and T4, we now have the effect of the fact that this pumping was also shut off. Okay? So this is what superposition allows us to do. Okay? And in principle, even if you had continuous pumping, you could conceptualize it as a series of small steps and effectively do this thing. Or you could try and do a continuous integration. But superposition then allows you to add the effects of different kinds of pumping. And this property also allows us to say what is going to happen when we have interfering pumpages. So if at a given observation well, if I have multiple wells pumping, because the same reason, the drawdown that is experienced by this observation well is the combined effect of the drawdowns of each of these pumping wells. Okay. So assuming that the observation well is within the radius of influence of these wells, we simply add the drawdowns as if each of those drawdowns were occurring individually and they get added up. And if these wells were also starting at different times, they were not all starting at time t equals 0, we would then, just as we did in the previous case, make this correction of t minus t1 or t minus t2, depending on when that pumping well started. So if you write this expression of this nature, notice that w of u, or this function, if t minus t1 is negative, that means this pumping hasn't started. Its effect would not essentially be felt. So we would simply know that when u is not making sense, negative, then w of u is going to be 0. And we also use this particular property of linear behavior to simulate simple drawdown, simple boundaries, I'm sorry. So because we now have this solution for what is going to happen at a certain distance, at a certain time, for a zero drawdown boundary, so let's say this is essentially a boundary over here, okay, which is a stream, a very large stream, so that the water level, let's say, is not affected because of pumping over here. It's in contact with this aquifer on this side. If I have a real well over here, which is removing water, pumping water out, now that my aquifer is not infinite. This solution that I had, the well function solution, assumed that the aquifer is infinite. So to simulate the effect of this boundary, what we are able to do is put an image well, which is perpendicular to the boundary and place the same distance away. Okay. And however, its sign is opposite of that of your real well. So if your real well is a pumping well, your image well, if you will, is a recharging well of the same strength. So if I'm pumping at a rate of QW, I'm recharging at the rate of minus QW. So what that does is, since each point over here is equidistant from both A and B, whatever is the positive drawdown occurring from pumping from A is compensated by a negative or a buildup, recovery if you will, of the same magnitude because of B. So any point on this boundary is equidistant from A and B. So those two drawdowns algebraically add up to be a zero drawdown. And mathematically what would mean is, if I'm looking at this point O, observation well, which is at a distance of R sub R from the real well and R sub I from the image well, then the drawdown that I observe over here is simply the superimposed effect of both the real and the image wells. So fairly straightforward. Same thing, not same thing, but a similar idea if it's an impervious boundary. An impervious boundary means it will not allow any flux. And again, we have the image well and the real well A, image well B. The image well is placed at the same distance from the boundary as the real well in a perpendicular line. But now the image well has the same sign as the real well. So both A and B, if A is pumping, B is also pumping well. Same magnitudes. Okay. And then at some observation well O, the actual drawdown that is being experienced is replicated or is modeled by the drawdown from the real well plus the drawdown from the image well. The real well is a distance of R sub R from the observation point. R sub I is a distance from the image well to the observation point, and you get this expression. And this is also, now it's a zero flux boundary. And these assumptions are valid as long as these boundaries are relatively straight. Otherwise, aquifer is infinite and so on. Any questions? Yes.
So what is the basic difference between this impermeable rock and the previous one? That minus sign came in that previous one.
Okay, so in this case, this is not an impervious surface. This is essentially, let's say, a very large river. So this large river is in hydraulic contact with the aquifer on this side. So it's this, therefore this river is actually supplying water to the aquifer. It's not impervious. So whereas the other case, it's not a river. In the next case, when we are doing an impermeable boundary, no flux. That's like a solid rock, and therefore it does not allow any water to come from this side of the aquifer onto this side or vice versa. So the boundaries are physically different. Any other questions? Can anybody tell me why, when I put the image well as the same sign as the real well? Okay, for this one, is it clear to everybody why having the image well as an opposite sign essentially makes this zero drawdown boundary?
Injection.
What's that?
Injection. We are adding water.
Yeah. If that is, I want to know why this, if the image well is the same sign as the real well, I'm simulating an impervious surface over here.
We are a rock boundary.
What's that?
It's a rock outcrop, solid rock.
Right.
Which doesn't have any pores or any.
Yes, the boundary.
Instead of keeping that, instead of keeping that imaginary, we can keep a no flow boundary.
True. Well, I guess my question is, why is it that having an image well with the same sign as the real well simulate a no drawdown, or sorry, zero flux boundary over here? Yes.
Actually, when we are considering the Lorentz equation, we are assuming that the R is infinity. The extent of the aquifer is large.
Yeah.
But here there is a boundary, impervious layer, means that whatever we are assuming, that is not true. So if you put same means sign well in opposite direction, the effect that what it will means the large extent means aquifer providers. For this one, it will counter that effect.
But why? It was countering the effect in the previous one too. What is happening to make that an impervious boundary? If you answer that question, we can go for T. Is that right?
Yes.
Yeah. Okay. I don't have a whole lot after this. So what is the answer to that one? Oh, good Lord. Okay. Anybody? What's actually happening? Why would that be an impervious boundary? What's that? Well, the professor's answer is like cheating. Anybody? All right, any one of you can answer then.
Basically, the snow flow boundary is basically a streamline. See, for a streamline to be there, so the flow line should be along the boundary, isn't it? So I can get the boundary, because if there were no barrier boundary, the flow line will be radially towards the pumping well. Okay, so to bring it back to this, so if I put another well which is at the same distance on the other side, and I keep pumping, so that also the effect of the image will also be towards its radial, so the resultant will be on the barrier boundary.
Okay, I think you are giving the physical reason, which is correct. I want to know the mathematical reason why that solution is giving us no flux. What you say is correct. It's entirely correct, but you're giving the physical reason. I want to know why mathematically that is working. Anybody? Okay, let me use the whiteboard because we haven't used it even once. So, let's say this is the soil surface. Okay. And this is my confined boundary. I have pumping well over here, pumping at the rate of 2 W. And let's say this was the initial piezometric head, my drawdown curve looks like this. Now I say I'm going to put an impervious boundary over here. So this upper curve is an impervious boundary. And perpendicular to the screen. So what we are saying is I'm going to put an image over here. Same sign, same stand, right? That's an image. So if the upper curve was homogeneous and there was no impervious boundary, I could superimpose the effects, which is what I'm saying, which means I would have a drawdown from this one, which will be, sorry, I'm not sure I can draw it very well. Something like this. And what I'm saying is anywhere in this real place, the real part, the total drawdown is going to be drawdown because of this is not, so let's say this location R, this is the drawdown from the, this is the drawdown from the real well, there's a drawdown from the image well, I'm adding them both to get a total. So what happens is, this curve, this drawdown curve, then basically add up. So what do we require for no flux? The water is going to move because of a change in the total head. dH, dr has to be non-zero. If I superimpose these two curves, essentially the combined drawdown curve is going to be like this because I have to do drawdowns. Because these two slopes are going to be exactly in opposite directions, at this point this has zero slope. And therefore dH, dr becomes zero and gives you mathematically why you get no flow. And you are giving a physical reason, but that's the reason why the image well thing makes it a zero drawdown boundary, because it changes it so that when you superimpose the two piezometric surfaces, because of the image in the real well, it will basically have to become flattened out over there. And then you get, all right, long-winded explanation. So the same idea can be used if you have multiple kinds of boundaries. You can have boundaries at right angles, they can be both impervious, they can be both zero drawdowns, and you would have multiple image wells. You would do the superposition. But the idea is that it's linear and that you're able to add drawdown effects. Okay, so we'll stop over here. I'm sorry we ran late. Any questions?
That should be explained from source and sink concept also.
What's that? I didn't hear you.
Source and sink concept.
Source and
Sink.
yeah. But what is that concept, Shankar?
Doing kinematics, I mean, source in double A, all this.
Source
Injection.
All
All the equipotential and varies.
Yeah, I think that is what Professor Hari Prasad was trying to say when he was talking about impervious boundaries. Yeah, so what you say is correct. I wanted a simple thing why adding these two is giving us zero flow mathematically. What you say is true. Physically, yes, I can see what is happening and how the equipotential lines and the fluxes would change. So, any other questions? If not, we'll take a break now.
Uh, Hello, am I audible?
Yes, sir.
Uh, in the previous lecture, actually, we have studied, okay, or the how the drawdowns when we pump a well in a confined aquifer or an unconfined aquifer or a leaky aquifer, what is the nature of drawdown, how it varies with, okay, with time. So, and we have seen the expressions for finding the drawdowns in each of these aquifers, okay. So to get the drawdowns, we know that we should have the aquifer parameters, isn't it? If I want to find out a drawdown in a confined aquifer, I should know what is the storage coefficient and what is the transmissivity. That is the those are the parameters which uh, characterize the confined aquifer. Similarly, in leaky confined aquifer, we have the hydraulic conductivity of the aquifer, the storage coefficient, as well as the leakage, okay, which is a parameter which is a combination of which involves the hydraulic conductivity, the aquifer, and the thickness of the aquifer, and the similarly in unconfined aquifer we have specific storage and the hydraulic conductivity and the delay index, okay. How, so when we pump a so how do we get these parameters, okay. So these parameters are usually obtained by doing the well pumping tests, okay. Pumping tests are always are required to find these aquifer parameters, okay. So basically what we do is that typically we pump a well in a pumping test, okay, and we observe the drawdowns, okay, with respect to distance as well as with respect to time. So we get this what we call it as the drawdown data. It may be with respect to time, okay, with respect to space or radial distance. So from this data, we have to infer what will be the parameters of the aquifer. So basically here, basically this pumping test analysis is nothing but an inverse problem where using the pumping test data, okay, time drawdown data, okay, at each of the observations well. So we will be finding the aquifer parameters, okay. So the pumping, usually a typical pumping test has a pumping well. Usually there will be a well. So these pumping tests are very costly tests. We cannot do it in laboratory like, okay. So what we have to do is uh, usually these tests are done by government agencies like state groundwater departments or the central groundwater departments or some research institutes, typically uh, catering to this type of uh, tests, okay. So the first one is usually a typical pumping test, okay, has a pumping well, okay. So what we do is when we do a pumping test, so we usually see that the water table is not, or water table or the piezometric surface is not affected by other pumpages nearby. So we tell all the people who are who are having wells near the well not to pump for a long time, so that the we get the initial piezometric level or the initial water table to be relatively horizontal, okay, so that there is no what is the source of symptoms in the nearby place. Then we will have a this system. We will have a pumping well, okay, and where we will be pumping the oil, and we will also be observing the drawdowns in the surrounding some 4 or 5 wells near this at different radial distances and at different directions. See, if we do this, what we do is we start pumping the well, okay, with constant discharge. It is also maintaining a constant discharge is also a very challenging task. Okay, because typically a pumping test is carried out minimum 3 to 4 days. Okay, especially if you have an unconfined aquifer. We know that when Professor Govindaraju told there is a usually a drawdown curve in a typically unconfined aquifer will have three parts. One is the first initially increasing part, and there is an intermediate part where the drawdowns are the rate of change of drawdowns becomes lesser because of the delayed drainage, and later on it will be increasing. So these to get these three limbs, so we have to do our tests for a considerably long duration. Usually a typical pumping test in an unconfined aquifer, usually you should do minimum 4 to 5 days. Okay, then only you will get this gas, otherwise we will not be able to get the proper listing. Okay, so during the test, what we do is the discharge is measured, okay, from the pumping test and draw down at each of these observation wells, okay, which are kept, okay, at different radial distances. They are also monitored, okay. So this data, we call it as the time distance drawdown data, okay. Initially, we will be measuring what is the depth of water table or geometric surface, and as we pump with time, so we will be monitoring how much water has gone down. So the difference will give me the drawdown data. Okay, this is a typical pumping test data we get. Let's see. It's not working.
What's like?
ये काम नहीं कर रही.
इससे करीब
ऐसे कर रहा हूँ,
ऐसे
कर दो. इस ये चला जाता है. ओके. So generally, इनसे पूछ लो. ये बेटर है. So usually a typical pumping test should have at least 6 observation wells, but because of the huge amount of money, it's quite expensive to do that. Usually a typical pumping test will have 2 to 3 observation wells and 1 pumping well. Okay, and also sometimes
How it works.
okay. So usually we will have a 2 to 3. So sometimes only if there is a constraint on money, okay. So you can also do a pumping test with only the pumping well itself. Okay. So that means you try to find the drawdowns within the pumping well. Okay. And from that you can also get the recovery. Okay. So the recovery data also. So that means once I stop pumping, okay, so the water will rise. So that data is called the recovery. Okay. So that data also we can use for finding out the aquifer parameters. Okay. So the main drawbacks of this is that, okay, the heterogeneity. See, basically the pumping test, okay, it gives an overall response of the aquifer. Okay. So the inherent heterogeneity is within that aquifer, it cannot be captured by the pumping test analysis. Okay. So the heterogeneity may not be captured, and if you are observing, especially if you are having only the data from the pumping well itself, so near the well, because the diameter is very less, okay, there is a possibility that the flow or the Darcy's law may not be valid. Okay, the Reynolds number may become quite high. Okay, so that is one more thing. And if you keep your observation wells too far, then the drawdowns will be very less. Okay, so that is also they may not be measured very accurately. So all these things should be kept in mind. Okay, while we design a pumping test. Okay, so it is good to have uh, observation wells not as close as possible to the pumping well, as also it should not be too far. Okay, so it should be at intermediate so that we can capture the okay uh, drawdowns quite measure the drawdowns quite accurately. So typically variations of drawdown in all the aquifers. In confined aquifers, usually the drawdowns or the drawdown levels are few hundred meters. Okay. In aquifer, in unconfined aquifer, it is in the order of maybe tens of meters. Okay. But in leaky aquifers, it is in between. Okay. So this the duration of the test also should be long enough to activate the parameters to be. That means you should do it for quite a long time so that you get the parameters properly. Confined aquifers. So in confined aquifers, what are the parameters which we try to estimate? The storage coefficient as well as the transmissivity. Okay. In leaky confined aquifers, you have the transmissivity of the aquifer, the storage coefficient, and the leakage, which is a combination of the aquifer and aquitard parameters. And basically, we should do our pumping test such that L gets activated. If you stop it before, okay, we may not be able to get this parameter at all. Okay, and in unconfined aquifers, we have four parameters to be estimated. One is the transmissivity. Okay, it is actually not the transmissivity; it is the hydraulic conductivity. S is the storage coefficient. Sy is specific yield, and 1 by L is the delay index. Okay, so these four parameters are to be estimated. So for this Sy, even in unconfined aquifers to get Sy and alpha, okay, so we have to do it for quite a long time. Okay, it requires. So what the data which we get when we do the pumping test is actually we will be noting down what is the radial distances of the observation wells from the pumping well, water, then that means basically the RWs, what is the pumping discharge, the time lay down data at each of these observation wells as well as from the pumping well. If you have more than one pumping well, okay, usually it is avoided, okay, but if it is there, then we also have to take care of how much is the pumpage from these wells also. So basically interfering pumpages, okay, and the radial distances of each of these observation wells from these pumping wells, that is also required for the pumping test analysis. The simplest is let us talk with confined aquifer. In confined aquifer, the parameters need to be estimated, or you know that storage coefficient and the transmissivity. So this Cooper-Jacob analysis, okay, it can be used effectively because here the what is that, the drawdown is a linear function of it's a simple function of t. So this avoids, okay. So if we can do it by either what is that, the type curve analysis, which we will be seeing later, and or we can use Cooper-Jacob approximate analysis to get these parameters much more easily, avoiding the use of what is that, the type curves. Okay, So we know that from Cooper-Joppa approximation, if u is less than this r square s by 40t is nothing but u. If it is less than 0.01, we can approximate s as a semi-log plot as, with respect to t. Okay, so s is given by q 4 pi t into log 2.25. So if I convert it into common logarithms, we get this. So when I write this in two parts, like log t by r square plus log 2.25 by t into s, because this is a constant, so s is a t by s versus t by r square is a semi-log plot. So what we do is you plot this here. So this we call it as a time distance drawdown analysis. Okay. So on the x-axis, you plot t by r square on semi-log sheet on semi-log scale, and here this is the drawdown. Okay. So here actually I'm taking the drawdown positively downwards, so that's why this curve is coming down. Okay. So otherwise, if I plot it up, this will be drawdown will be increasing with t by r square. So you plot this curve. That means basically these dots or or the drawdowns at different observation wells, okay, at different times. Okay, so for all this we can get t by r square because we know t and we know r. So and the corresponding s, you plot it. Okay, so it plots as a straight line, okay, on semi-logarithmic paper if u is less than 0.01. Okay. So usually what happens is, because for u to be less than 0.01, so our t should be a little longer. So the initial part will be deviating from this straight line. So we have to ignore that. We should not fit the straight line, taking the initial points also, because at that point this Cooper-Joppa approximation is not valid. Okay, so you have to plot this straight line taking the later points. Okay, so then plot it. So then we can find out T, the transmissivity, as 2.3 q by 4 pi delta s, where this delta s is the change in drawdown for 1 log cycle. That means, let us say I take this 1 log cycle means, let us say this is 1 and 10. So take the corresponding s values for 1 and for this is yes 1 and 10. Okay, so you find out what is this. Okay, or you may take 10 at 100. Okay, so use this expression. So you know delta s, t is q is known to us, so you can find out what is t. Okay, so once you know t, so how do we get s? S is by this formula 2.25 t by t into t by, because we know t, so t by r square is also known, so you can find out this. Okay, so where delta is the amount of drawdown over 1 log cycle, t by r square is the x-axis intercept, where the extrapolated best is the intercept at the time. So you can find out t and s using Cooper. So basically what you have to do is, you have to plot on a semi-log sheet t by r square versus the drawdown s. Okay, so then from that data you can use these two expressions, okay, to get the transmissivity and the storage coefficient. Another one is time drawdown analysis. Okay, so here at a particular R, because we have 2 or 3 observation wells, at each of these observation wells, I plot S as a function of time, T. Okay, so this is for 1 hour, this is for second one, and this is for the first observation well, second observation well, third observation well. Okay, so When R is constant, we can write S is equals to 2.3 Q by 4 pi T log T plus 2.3 Q by T log this. Okay. So since R square ST 4 TD by is less than this, so T will be greater than this. Again, we use this formula. Okay, T is delta S is the amount of gradient for one log cycle. So find out T. So knowing T, you find out S. Okay, by taking any one point here, take T naught. Okay, so for that T naught, so you know T R square, so you can get the this. So the main or drawback of this is that initial data is not utilized, so there is an information loss. Okay, advantage is it is simple to do. Okay, because you are fitting a just straight line as compared to a curve matching, which we do in what is it the type curve analysis. Okay, so even though this is a very simple one, usually the people the values which we get from this Cooper Jacob test is not as accurate as we do for using the type curve analysis. Okay, so the type curve analysis we will see later. So one more thing is another important test which we do for pumping test analysis is the recovery test. So basically, in a typical recovery mm, test, what we do is we pump the water for some time, okay, and we stop pumping. Then we also record how much time it takes to recover. That means for the water table or the piezometric surface to come to its original level. Okay. So let us say I pump it for 6 days. Let us say 5 days. Okay, I stop pumping. Do you think that another 5 days will it take to recover, or will it take less time? Let us say I have pumped an aquifer. So the drawdowns, okay, water table has gone down, okay, or the piezometric level, let us say for 3 days. So I stop pumping. Will it take another 3 days for it to come to the original, or it will take less time? It will be taking less time. Why?
Flow might be say that it not stop us. It will be continuously.
But why it will take less time? See, usually, typically, it will recover in 4 to 5 hours. Even though we have pumped for 3 hours, 3 days, okay. So if I allow it to stop it, so within 6 to 7 hours, you will get back the full recovery. See, what is happening is during the recovery stage, the entire aquifer is contributing. Okay, but whereas when we are pumping, so the aquifer far away from the pumping well will not be contributing. Okay, so that's why the drawdowns will be more at the so as time goes on, but when you do the recovery, because the affected aquifer portion will be contributing, so that way the recovery will be much faster. Okay, so this is basically a typical residual. So the build up during the recovery, we call it as a residual drawdown. Let us say from here to here, let us say initially the drawdown is zero. The drawdown is zero. So let us say the piezometric level is here. Now it has come down up to here. So when I stop pumping, so it will again recover and it will reach the original piezometric level. So this time, okay, is quite less as compared to the, so the recovery period is considerably less as compared to the pumping period. Okay, so this, the drawdowns or the buildups during the recovery, we call it as the residual drawdowns. Okay. So the principle of superposition again we can apply here. Okay. So that means let us say I have done my I have started pumping and I have done my pumping up to time TP. Okay. So TP basically refers to the time up to which pumping has taken place. At TP I stop pumping. Okay. And I allow recovery. Okay. So the drawdowns, the residual drawdowns, okay? Yes. So I am just to differentiate the residual drawdowns from the initial drawdowns. We are putting it as S dash. How can I compute S dash? S dash we can write it as Q by 4 pi T into W. This is the well function of here this T starts from 0. Okay, but whereas for this second one, the T starts from the origin is TP, T minus TP. Basically, if you see here, so basically when Professor Govindaraju told when you have time varying pumping, basically what we are doing is I have a discharge of Q up to time TP. After time P, the discharge I am stopping the pump, so that means my discharge is 0. So mathematically, how can we get this scenario for time after TP? You add Q and subtract Q from TP. So the original Q will continue from T is equals to 0 to this thing, but the negative value for which why we use minus Q, that will start from TP. So that here we are adding or we are subtracting. Okay, so that's why. So this will go on decreasing. S dash will be go on decreasing. Okay, so because this value will be increasing much faster as compared to this, so this will be after some time this becomes 0. So that means the residual drawdowns are 0. So this data, the residual drawdown data, can also be used, okay, for finding out the. Basically, this is a very good test for checking whether the transmissivity which we get from the pumping test analysis is very correct or not. Okay, basically the recovery really gives you a very good information about the transmissivity. Okay, so S naught, so the equation becomes like this when we write this W S dash is equal to 2.3 Q by 4 pi T and to log of T minus T by P. So you plot the cycle, you plot the graph versus time ratio T by T minus TP versus the residual drawdown. Okay, so you get this. So again, you have a Cooper-Jacob equation. So this you can use it to get the transmissivity. Okay, the transmissivity. So the residual drawdown per log cycle you take delta S dash and find out T. Okay, so from the recovery test, what you can do is you can get T from two ways. One is using the time drawdown data before we stop the pumping. Okay, and other one is by using the recovery data after we have stopped pumping. So these two, if you are getting close, okay, so that means your analysis is over. But otherwise, there may be some other causes for this thing that I'm not sure what can be the reasons. But so this is one way we can check whether we are getting a proper T or not. Okay. Similarly, once we know this, we can use this expression to get S. Okay. even though this Cooper-Joppa method is a very simple method to estimate this parameters T and ST for confined aquifer, but usually we go for type curves analysis for finding out the uh, for finding out the parameters S and T. So we know that the Thies equation, this basically gives an unsteady state drawdown, okay, as a function of T and R, okay, where S is equals to Q by 4 pi T into W, where W is the well function. Okay, actually, U should also be one. Okay, somehow it's not written. Sorry. So log x, if I take the logarithmic, so this will be log of Q by 4 pi T plus log of W. Okay, so this W, if you see here, what is W? W is nothing but where U is equals to R square ST S by 4 T and R square. This term, if you see here, this is a constant, isn't it? See, if I write log s is equals to log q by 4 pi t plus log w, only this will be varying with time and distance, but whereas this is constant because q is constant and the aquifer parameter t is constant. Okay, so taking log again, if we can write like this, log r square by t is equals to log u plus log 4t by s. Again here also, only this will be varying and log 4t by s, this is a constant. So as t increases, drawdown increases, as r increases, s decreases. So we can write log w is equals to log x minus log q by 4 pi t. So this is a constant, and this subtracting log q by 4 pi t from log s, we get this, which is a constant. This means that, okay, similarly, you see here, this means that log w versus log u type curve is parallel to log s versus log r square by t, okay, by some value, okay. So basically they are parallel, okay, but they are lagged by some constant distance. They are basically, this lag is like this. There is a constant positive shift on x-axis of type curve from data curve by an amount log 40 by s, and a positive shift of log q by 4 pi t of type curve from the data curve on y-axis. That means if I plot s versus t, okay, on a log and this u versus wu curve, okay, so they will be parallel to each other, but there is a shift, okay. So this shift will be a, so if I can arrange my type curve, okay, by keeping parallelly the time drawdown curve and the type curve, okay, and I shift it. So if I make this shift which is equal to this, then the both will match. So this is the basically what we do here is, see here what we did is we have plotted 1 by u. 1 by u is nothing but what is u? U is equals to r square s by 4tt. So 1 by u versus wu. We plot it, okay, and on the same graph means I also plot s versus t by r square. This is s by t by r square is a rising curve. 1 by u versus w is also a rising curve, but only thing is that there is a shift of log of 4t by s on x-axis and log q by 4 pi t on y-axis. If I keep, usually what we do is we plot this type curves on a tracing sheet. Okay, and we put this tracing sheet, okay, on the time t by r square versus s. Okay, so keeping the axis of both these graphs parallel to each other. That means we are not tilting it. Okay, if I shift my this tracing sheet so that the drawdown data, okay, matches. It is very difficult to get a exact match. Okay, so it matches most of the data points. Okay, where s by t, s versus t by r square. Okay, so at that point, so you just keep, okay. At that point, what you do is you mark, take any point on this matched position, take mark, you let us say I take this point, match point this, okay, this here, okay. So let us say I get t by r square for this match point from this graph and 1 by u from this. Similarly, I get s here and the corresponding wu. So that means basically I will be having 4 values: wu, 1 by u, t by r square, and yes. Okay. Yes.
Well function is nothing but W of U as such.
Yes.
What is meant by U, sir?
U is r square s by 4t.
What is the name of it?
There is no name given to you. I think there is no name for it.
So W of U, U is just values going from 0 to infinity. And W of U is just a function which says for different U values, it's a fixed function. What we, for our purpose, we calculate U as SR square over 4 capital T small t. So,
There is, yes.
so we could have called it W of X for all that it mattered.
Basically, W is a function of U, but this W is called well function, but there is no name given to U. Basically, this U is a function of course, r square st by 4tt. So, which really represent the what is the aquifer information? Okay, we can say.
Well, consider in the context of groundwater,
Uh,
there is an expansion there.
huh?
It's an exponential.
Yes. Okay. So from the type curve, okay, from the rising curve, you get the log W versus 1 by U. So I know what is 1 by U? 4tt by r square. R square HP. Okay. So from this, we know what is S, what is W, what is T by R square, and what. So we will be noting this. So using this, we will get the parameters. Okay, T and ST. Okay. So basically, we know that using S and W, because S is equals to, we know that Q by 4 pi T into W of U. Okay. So S I know, W I know. So Q is known to us. So first we will find out T. Okay. Knowing T, so that basically using S and W, we will be finding T. So once we get T, okay. So 1 by U is R square by S by 4tt. So using these two, we can find out ST. Okay. So this is how we find out. So basically, if I plot 1 by U, this will be a rising curve. But if we use log U, so that will be a falling curve. Usually we follow this. We will be plotting W versus 1 by U as a type curve. Okay. Because whenever we plot the drawdowns will be increasing with time. So to be consistent, we plot W versus 1 by U rather than W by U. Okay. So this is a similar one. Again, see here what we did is, here we have plotted T by R square time distance drawdown. Okay. So that means basically we are taking at different radial distances of T by R square because, okay, so and we are plotting it. So here, let us say I have only one well, okay, so there we take the time drawdown analysis. That means at that radial locations, I plot S as a function of T, okay. So here also again the same thing we can use, okay. So we can find out the okay. If somebody can do distance drawdown analysis, that can also be done. Okay. So basically, you can use this type curves the way you want, depending upon how you have performed the test. Okay. So various combinations we can do, and we can get the transmissivities. Okay. But in the leaky confined aquifer, okay. So this is much more because now we have one more factor L, which is a combination of the aquifer and the aquitard. Okay, so there will be instead of having one type curve, you will be having a different family of rising curves for different values of R by L. We know that uh, W is now not only a function of U, but it is a function of R by L, where L is equal to square root of Ct, which really takes into account the effect of leakage, okay, on the pumping, okay. So for a curve of R by L, R is constant. So you have to, here what you have to do here is, okay, only one of these curves, okay, will be matching with your time drawdown data. Okay, when you plot S versus T and when superimpose this, okay, on your data, not all curves will be falling. Okay, so only because we know that when we pump a well in a confined leaky aquifer, initially the drawdowns will be more, okay, then afterwards there will be a leakage from the aquitard, okay. If the leakage is more, the drawdowns, the rate of increase of drawdown will be less. So that means you okay, it will become a little flatter. Okay, so the amount of flatness depends upon how much is the leakage. If the leakage is very small, it will not be as flat. Okay, but as the leakage is high, it becomes flatter because the drawdowns will not be increasing as much in the aquifer. Will not be increasing as much because there is a contribution from the aquitard. So only one or two among this. So you have, because it's all subjective, so you have to pick up that curve which is closely matching with the time drawdown data. From that, for that you find out what is R by L. Okay. So from this information, you can find out what is T, what is S, and what is the corresponding L. Okay, this is how we use the for leaky confined aquifer. Okay, so like this, you see here. So respectively, till one of the RL curve matches the data curve. Okay, the curves are matched with the two axes parallel respectively. Till one of the R by L curve matches the data curve. Okay, use that to get. So match point coordinates, what we will be getting is T, 1 by U, S, W, and R by L. R by L known from the match curve, R is known, so you get L. Okay, L can be computed, hence S and become known from the active curve. So this is a typical one. So the most difficult one is getting the parameters of an unconfined aquifer. Okay, so this is really a very experienced people can get really to do a good job of getting the accurate values or estimates of this. So we know that in unconfined aquifer, what are the parameters which we have to estimate? One is the hydraulic conductivity, another is the specific yield, then the storage coefficient. Of course, even the compressibility is quite small, but even that also should be estimated. So the storage coefficient, the specific yield, then hydraulic conductivity, and also the delay index. How fast or the what it releases from its storage. Okay, so usually this alpha, this 1 by alpha, okay, is a measure of the delay index. If the delay index is more, that means, let us say delay index, it has a units of time. Okay, typically for a sands and all, sands and gravels, okay, this L varies from for gravels it will be very fast, maybe 1 hour. For sands it will be 6 to 7 hours. Okay, but it clays it may go for days. That means if I pump a well in a clay material, okay, so the time which is required for it to totally dry, okay, is 4 or 5 days. Okay, that means basically it will be sending it to the storage very gradually. It will not become dry very fast. Okay, so basically that alpha is also an important factor over 1 by alpha. Okay, so from the pumping test analysis, if we have to get this alpha, so you have to do it for a considerably long time. Okay, so basically, as when Professor Govindaraju showed you one figure where you have a early time, there will be a very short increase in the drawdown. In the intermediate times, there will be a the rate of increase is quite less. So this is what we call it as where the delayed drainage is contributing. Afterwards, once this delayed drainage is completely this, then there will be a rising curve. Okay. So if you have to get all the 3 segments of the pumping test, so you have to do it for a considerably long time. Okay. So if somebody, so for that, the what is that? The drawdown we can write it as Q by 4 pi T and F. When here UA, actually this should be UY. Okay, UY R by B and N, where UA is for early time, where we write R square ST by 4 dt. For later times, UA is equals to R square SY by 4 dt. Okay, so this so usually we write it like this: W of UAY. A corresponds to early time and Y corresponds to later times. So when I use when you plot this curve, okay, on the time drawdown data, okay, so you will have these 3 segments. So let me also write on this board. So basically, if I plot T versus S, okay, is a function of time. So you will get a curve like this. So like this, it's not, it is rising community, but the rate of increase in the intermediate stages will be less, okay, because there is a contribution from this. So if I want to analyze this portion, okay, so my U is, because here in this time, during this time, the compressibility effects are much more dominant as compared to the delayed component. Okay, so here I have to use R square S by 4 PE, where S is the storage coefficient. Okay, for this portion, if I have, so this usually we call it as UA. Okay, and this is UY. Okay, is equals to R square SY by 4tt. Okay. In this is the intermediate. Here both will be influencing. Okay. So this see here you can see. So basically this depends upon these curves. Okay. So there are different curves. You can see here this curve for 1 by u by a, and this is for 1 by u by y. For any other thing, so you will get these curves for different values of r by b. Okay. So what is b here? B is I have forgotten to give the expression for b. Let's see. So I will just let you know because somehow
It's in the previous presentation.
previous.
It's the t over alpha sy square root.
Yeah,
of alpha.
basically this. So b is b what's it?
Alpha into sy.
Huh?
Alpha into sy.
Okay.
Exponential minus alpha e minus e.
This one.
No.
No.
It's t divided by alpha times sy, the square root of all that.
Can I see?
Of course.
Oh. Square root of e into alpha into s. Here, this alpha is coming into picture. Okay. And, so basically this r by b value. So your drawdown, okay, will be in between this ua and uy. Okay, depending upon alpha. Okay, what alpha? It will be following one of these curves. Okay, so for us to estimate t, okay, and st and sy and alpha, what we have to do is actually it is not a simple procedure as in confined aquifers. First, what you have to do is you plot the curves. Okay, so this is what we call it as a type curve for unconfined aquifer. Okay, so this you have to plot it on a tracing sheet. It's available. Okay, oh. Then you plot T versus drawdown, T versus S. Okay, so this looks like this. So when you superimpose that on this, okay, it will be following only one of these curves. First, what you have to do is, first you try to match the earlier portions of this curve with the earlier portion of the time drawdown curve, get the t value and st value as we did for confined aquifers. Okay, so you will get t and st from there. Then the first one is here, match segment 1, and there are two match points in case of unconfined aquifer. The match one is segment 1 and 2. You find this. Okay, match point coordinates will be 1 by u by a, w, t, s, and r by b, which is the storage coefficient, the transmissivity, and B value. Okay, B is nothing but the T alpha by S1. Then segment 2 and 3 match point coordinates will be 1 by uy, w, t, s and r by b. Okay, yields sy, p and b. So basically the value of t which you get from those both analysis should be same. Okay, otherwise you have to do many. It is very difficult to get both of them same. So you have to do a lot of iterations. Okay, so that way this types of matching is a very means only the experienced people can do it. But fortunately now we have a lot of other techniques have come where you can avoid this because it's very subjective. Before that, when the computers were not there, so people used to do it, but now because we have routines which can directly give these values. Okay, so this is how we can do it. It's quite a tedious exercise. It's not that simple, so we should have it. So, any questions?
By alpha is delayed.
Yes.
What is meant by only alpha?
Yeah, alpha basically when we write it, no, actually we write fy into e power minus alpha t. Okay, so basically what we are saying is ultimate value which the amount of what leaves will be sy, but that will be delayed. Okay, it takes time. So that we have expressed this as e power minus alpha t. Okay, so this alpha has what will be the unit of alpha? Because it has to be non-dimensional, so this is 1 by alpha has 1 over t. Okay, so usually we don't express this, so we take it 1 by alpha. It gives a measure of if 1 by alpha we have a time unit. So if 1 by alpha is very high, that means it takes long time for the soil to release water. Okay, if 1 by alpha is small, that means it almost instantaneously gives release this water. Okay. Any question?
Do you want them to bring their laptops today?
Yeah, you can bring laptops.
Please bring the laptop.
Whoever is having, okay. Do this.